The pigeonhole principle is a powerful tool in mathematical research. Suppose you have n objects and m places to put them. If n is greater than m, then two or more objects must be put in the same place. The pigeonhole principle is frequently used in modulo arithmetic. If you're working mod n, then any computation can have only one of n possible values after being reduced mod n, namely 0 up to n minus 1. So any function must repeat values. Or must it? If our function takes input values mod n and outputs values mod n, then the pigeonhole principle doesn't apply. There are only n pigeons, input values, and n pigeonholes, the output values, so there's no requirement that any repeat. Now let's consider an exponential expression like 8 to the 6th mod 6. So remember, when working mod n, you can always reduce to a number between 0 and n, and since 8 is congruent to 2 mod 6, then 8 to the 6th is congruent to 2 to the 6th. Now we might think further and say, well, since 6 is congruent to 0 mod 6, could we reduce 2 to the 6th as 2 to the 0? Well, we note that 2 to the 0 is 1, but 2 to the 6 is 64, which reduces to 4, and they're different. Consequently, 2 to the 6 is not 2 to the 0, and so even though 6 is congruent to 0 mod 6, 2 to the 6 is not congruent to 2 to the 0. And you might wonder, what happened? Well, why did this happen? While it's true that 6 is congruent to 0 mod 6, this is only true provided that 6 is a number mod 6. What do we mean by that? Well, note that 2 to the 6th is really the result of taking 6 factors of 2 and multiplying them together. And the thing to realize is there is no 6 in 2 to the 6th. So that means that the 6 as an exponent can't be reduced mod n. Now consider a sequence of powers, a squared, a cubed, and so on. We might be able to reduce the base a mod n, but not the exponents. So this is an infinite sequence of numbers. Now if we reduce these mod n, there are only a finite number of values they can be congruent to, and so two of these values must be the same. There have to be exponents where I to the I is congruent to a to the j. Now, from a to the I congruent to a to the j, it's tempting to conclude that we can divide out this a to the j, and so we get some power congruent to 1. But we've already seen before we can't do this unless the greatest common divisor of our base and our modulus is 1. But you can assume anything you want as long as it's explicit, so let's assume that it is. Consequently, suppose the greatest common divisor of a and n is 1. Then for some k, a to the power k must be congruent to 1 mod n. So a useful strategy is to start with primes. Suppose n, our modulus, is prime. Then, provided that a is between 1 and n, the greatest common divisor will be 1, so a to the k congruent to 1 has a solution. And since 1 to the k is just 1 for all k, we'll assume that a is between 1 and n. Now, at this point, we might gather data on the least value k that makes a to the k congruent to 1 mod n. For example, if we work mod 7, we find the least powers are going to be 2 to the 3rd congruent to 1, 3 to the 6th congruent to 1, and 4 to the 3rd congruent to 1. But if we work mod 31, we find the least powers skip around quite a bit more. 2 to the 5th is congruent to 1, but 3 to the 30th is congruent to 1. 4 to the 5th is congruent to 1, 5 to the 3rd, 6 to the 6th, and 7 to the 15th. So there's no obvious pattern to the least power k for which a to the power k is congruent to 1 mod n. So rather than try an experimental approach which seems too messy to give us useful information, let's try a theoretical approach. What if k is the least power for which a to the power k is congruent to 1 mod n? We'll see where that goes next.